Thank you, Sebastian, for a fascinating talk. Next, please welcome Kartik, Director of Perception and Robotics R&D at Intrinsic, an Alphabet company, for his talk on scaling intelligence, leveraging functional AI to shorten the time to value in production. A two-time founder who pioneered computational imaging in mobile cameras, Kartik leads Intrinsic's R&D in foundation models for robotic perception. So everybody, Kartik.
Thank you. And I think it's working properly. So good afternoon, everyone. I think Sebastian's talk was really interesting because it sets up a lot of the background and context and some open questions, some of which I might be able to offer some more insight into given what we are doing. So scaling intelligence. So before I get into what this is this working? I'm not able to forward the slide.
Oh, okay. That's right, but you should go down. Yes, down.
Oh, yeah. Okay, got it. So what we are doing here, we are a group in Google. We are a robotics group in Google. And what we are doing here is building a platform, a software platform for democratizing robotics. And as anyone who's ever programmed a robot for any kind of solution, it's actually very difficult to actually get the robot to a level of proficiency that you can actually deploy it in production. It takes a long time. In reality, I think it takes anywhere from 6 to 9 months. And the more complex the solution is, the longer it takes. So the platform that we are building is essentially it manages the entire robotic life cycle of the robotic solution through a very metrics-driven process for building up the foundation models that power the capabilities in the platform. So what we are building this platform for is to be able to scale these solutions. One of the things that you have in SaaS applications, which is land and expand, you build a solution, deploy it with the first customer, and once the first customer is satisfied with what you have, you can then scale it across 100 other customers because there's really no additional work that you have to do in going from one customer to the next. And that's invariably not the case in robotics because of a lot of the environment variables that change from one solution, one site to the next. And in a lot of, even within the same particular solution, high mix refers to when the parts that you're dealing with or the lighting that you're dealing with changes quite rapidly. And there's a very high throughput, which means the volume of parts going through the manufacturing process is quite high. And to be able to do this, your models have to perform at a very, very high level of reliability, 99.99% usually. And in some instances, we even have to get to 4 nines. And the challenge is, as we all know, AI models are probabilistic. Hallucinations are quite common with foundation models. And 95, it's very easy to get to about 80, 90, even 95%. But to cover the gap from 95 to 99 is extremely hard. So how do you get there? So I'm going to play 3 videos here. This is from the laser cutting-based sheet metal industry. And this is basically manufacturing of sheet metal parts, which are ubiquitous. For example, this building contains a number of sheet metal parts. And every sheet metal that comes through, which is about 3 to 4 meters in size, the laser is actually cutting hundreds, if not thousands of parts. And the geometry of these parts actually change from one job to the next. And that's really what high mix refers to. And in reality, while the animation here looks very nice and the parts are very neat and ordered, in reality, invariably, it's not the case. The parts are often grimy, it's got oil residue in it, it's got dirt in it, the look and appearance changes, the lighting changes. And when the parts fall on the base from which you have to pick it up, there's often they fall on top of each other and sort of nicely ordered as in this animation. This is another video from the CNC machine turning world. And here you have multiple problems. You have the variability problem, which is really the shifting customer requirements when it comes to part size, when it comes to the in-feed and out-feed, whether it's singulated, cluttered, or stacked. You often have the operator having to get involved in terms of the part preparation as well as flipping the part over or changing the vice. And every job actually requires a different sequence of steps that has to be orchestrated, which means it's a bespoke orchestration that you have to do. So as you go from one customer to the next, everything changes and you have to do bespoke programming again, which kind of limits your scaling capabilities. And then finally, a very ubiquitous application like bin picking itself also has multiple dimensions, and each of these dimensions have a number of variables. You have the object to be grasped, you have the environment in which it has to be grasped, whether it's singulated or cluttered, and finally, what do you do with it once you pick it up? Is it going to be just stacked? Is it just going to be thrown into a bin? Is it going to be inserted? Is it a tight fit insertion? So the dimensionality of the problem that you're dealing with is very, very high. And getting a foundation model to work across all these different dimensions at the level of reliability that production is very happy with is not an easy problem. So some context here, and I think most of you probably already know this, large language models are a type of foundation model that's trained largely on text. You have foundation models that go multimodal. They involve not just text data, you have video, you have images, you have audio. And finally, generative AI is really about creating new data or content by using the foundation models as the underlying structure for you to generate these new capabilities. In the early days of AI, you had to train a model for every new object that you actually got through your assembly line. Every time the object geometry changed, you had to train a new model to detect it. If you were looking at picking it up, the pose estimations had to be done per model, and this doesn't really scale. And so foundation models allow you to scale these capabilities so that it adapts to the changes in the geometry of the object, the size of the object, any other environment variable that you might be experiencing. And so it allows you to scale much better. But the challenges, of course, it comes down to the accuracy of how the foundation models can exhibit without the risk of hallucinations. There are any number of these models available in the open source world. There's CLIP, which is contrastive language, image pre-training, which is really about aligning images and text through learning shared representations. There is a segment anything model from Meta, which is based on bounding boxes, points, and mass. And then you have OWLWIT, which is open world localization. As you can see from the GIF here, it allows you to, for instance, enter a text and automatically have the model detect the object in the image. So the problem with open world localization or with any of these models is that these are all trained on a whole bunch of data that's available in the open source that's very representative of everyday objects. So you take one of these models and you try to apply it to the industrial objects that you encounter. And does it work? It actually doesn't. In fact, the accuracy level goes way down. And the other problem is a lot of the industrial objects don't have an easy way to refer to it. You don't have text associated with it. The geometries are very complex. And being able to describe it effectively requires a different language, which is either CAD or images. So we looked at a number of models out there to see what would work for the work that we were trying to do, or the platform that we were trying to build. And what we saw was a lot of the models, for instance, these are models that compute the pose of the object. The pose of the object determines the orientation of the object in 3D space. And they end up, it's actually an ensemble of many open source models strung together in a pipeline to create the final pose. Now, this has several problems. And the problems are you have kind of rigid interfaces between all these models. You're trying to hack them together, and that kind of limits the generalization that you can enable. There is also the latency, because the more stages you have in your model pipeline, your latency is much higher, the cycle times become worse. And so what we decided is to build the model from scratch and see how it did, right? So if you look at the last row, that is the model that we have that's currently going into production. It's already getting deployed with several of the industries. And that has only two stages to it. The first stage is a detection stage, and the second stage is actually a refinement stage that refines the output from the first stage. And it's also the stage which controls the hallucinations that might occur, because that is something that you cannot prevent. So this is a video that kind of shows the performance of our model in a number of different adverse lighting conditions, background variations, clutter, appearance, and you can see the complexity that you have to deal with when, there's often the expectation that in a factory where you're in a controlled environment, which is supposedly much better than being in the wild, like in autonomous navigation, you can actually get more controlled conditions. But that's not true. You get some very adverse conditions in the factory as well. So we didn't design this model to actually win a lot of challenges that are conducted in these conferences. We designed it to actually deploy it in production. But on a whim, when we had the model completed, we decided to take part in what is called the BOP challenge. This has been run for the last 7 years. And we ended up winning pretty much every category we entered, even though we did not train for any of the performance parameters that were part of the challenges. So, and when we saw this, we noticed that there was actually a big gap between how foundation models in the open source are trained and what we did to actually deploy these in the real world. And I thought that was pretty instructive to actually outline here. So there are 5 reasons why our model did so well. One is the sensing part of it, and then the metrics that we end up using to drive the iterative improvements of the model. The data distribution, which Sebastian talked about, there's a big distribution gap. How do you address that gap? And then inductive biases, and finally the long tail problem, which invariably happens with all of these models. This is a concept from information theory, which really talks about the data processing inequality, which is, all it says is that every time you take a signal and you process that signal, the amount of information in the output signal or the process signal is actually less than what you had in the input. So, which means that every stage of your pipeline, you're actually losing information. So the only way to maximize the output accuracy is either you increase the amount of information that you're capturing, or you limit the number of stages, the amount of processing you do on the information that you do capture. So what we saw is all of the existing approaches, they actually take the image. There's a depth information that comes from a 3D camera. You detect boxes, you create your hypothesis, and then you refine it. And the problem with this approach is the process of actually estimating the depth, which is through correspondences, is actually very error prone. That's actually still an unsolved problem. You don't have any solution out there that'll work in every situation under every constraint. And that's the nature of the current status with depth estimation. And given that you actually end up using depth estimation to compute output, it's not surprising that there are times when these methods actually fail. So what we did is we decided to discard depth. We used multiple images, and we decided to compute pose, or let the system learn the parameters that it needed to learn to estimate the pose. And this approach seemed to serve us pretty well. The metrics are another thing. So precision and recall are often 2 of the metrics that are used. And in this particular case, the precision and recall are measured against the 3D object geometric precision, as well as the 2D look accuracy. And these metrics are good in itself. But when you only focus on the recall, you actually have a problem in that the hallucinations are not controlled. And so what we did is, instead of relying on just the recall, we actually looked at the precision, where we ended up penalizing any hallucinations that happen. And this is really important because the model has to work in the presence of noise. Foundation models have to work in the presence of noise. And it has to be able to recognize objects that they haven't been trained on at all. And that's actually very difficult as well. So the other thing is the annotations. When you create the data, you have to create annotations. These annotations provide the ground truth information. So the annotations are mostly what we find in the public domain is that they're all hand annotated. And hand annotations are actually error prone. And the graph on the left, for example, shows a graph of the estimated model performance on the x-axis against the true model performance on the y. The blue line in the center is the ground truth. And you'll notice that the three colors on the lower right side represent the ground, the hand-labeled annotations, which are significantly away from the ground truth line. So what we did instead is we automated the process. We used precision-guided kinematic movements of the robot and used the robot to generate the ground truth information. And I don't want to go into the details here. And you can see the automated values line up very close to the ground truth because we can take a number of measurements with the robot and we average them. The data distribution is another problem. Many of the models that I mentioned earlier, they are all using a lot of the data that's available in the everyday objects in the world, and they don't really represent the kind of data you find in the industry. So we generated our own data, and here we actually use synthetic data. There's a lot of debate going on about how difficult it is to get data for robotics, which is true. But for a number of the robotics use cases, we find that you don't really need real data. And so we generated all our data synthetically. And this was large, about 110,000 CAD models. About 10% of that was industrial data. We also used the open source data that's available in the world. 1 million images, 8 billion tokens. And we focused a lot on the realism of the data, so photorealism was very important. And what we also found that while the metrics and the data distribution gap is important, the public benchmarks are not quite up to what the amount of data the foundation models actually need to perform at the level that they need to. So in terms of object types, the images, the object instances, you'll find this, our benchmark usually ends up being at least 1 or 2 orders of magnitude, which is more than the public benchmarks. So finally, we come to inductive biases. The world of AI changed once we moved from CNNs to transformers. And one of the advantages of the transformers is that the cons are it needs a lot of data, but the pros are if you can provide the data, the amount of learning that it can do is pretty significant. And it doesn't seem to stop. It continues to grow as you throw more data at it. So in the CNN world, there are what are called inductive biases. These are actually priors that you would give to the CNN to help the CNN converge faster to the final solution. Now, while this may create an advantage in terms of the performance floor, it also creates a problem in terms of the performance ceiling, because any pattern that appears that's outside the data distribution that you're providing in terms of the inductive bias, it's not able to learn. So transformers allow you to generalize better across domains, it scales faster, and it also avoids the human-centric errors. So I'm running out of time. So let me quickly go to the last slide. This goes into a little bit detail on the actual pipeline that we end up using in the model. But the long tail problem really comes down to getting as much information from the customer and using the customer data to fine-tune the model. And this, I don't know why this video is not playing. Here's on the left-hand side, you actually see an image that is one of the leading models in the open source world. And you'll see that the 3 or 4 of the objects that it actually detected are not correct. And the difference between the left and the right is the left is actually using the depth information to converge on the data, and the depth information being incorrect causes these hallucinations to happen. So let me just get to the last set of conclusions. Essentially, transformers are the key technology in building foundation models. Data distribution is really important. You want to curate the data for the domain that you want to deploy your models in. Metrics matter, the right metrics matter, but more importantly, the right benchmarks matter as well. You want to eliminate the inductive biases because the transformers can learn more without the inductive biases. And finally, the loop that probably never ends is to validate, validate, validate. With that, thank you. Yeah.